Assalamu alaikum students. Welcome to the lecture 3 of your engineering drawing and graphics course. And in today's lecture we will be talking about the object features, the projection theory, orthographic projection, multi-view drawing, glass box concept and projection system. You are already familiar with the 2D projection technique concepts as you have already done the labs. And you know that in projection technique what we do, we actually draw different views of a 3D object. Like as you remember, we drawn the front view, the top view and the side view. So now what we will do, we will just go through the theory, that what's the theory behind doing all this. We already know the importance of doing that. We covered that in lecture 1 and we said that we do this to get the correct size and shape, to get the correct size and shape of an object. And this correct size and shape can then be communicated to that machinist or any other person working using that drawing. So to get the correct size and shape of a 3D object, we draw 2D views of that object. So for that purpose, what we will do first, we will first define what are the common object features. If you are taking a certain 3D object, what will be some common features of that object. Then what is the projection theory, what is the theory behind drawing these 3 views, and what is orthographic projection, what is multi-view drawing, what is the glass box concept, and what is the projection system. So these all these topics are related to these 3 views that you have drawn on your sheet in the manual lab that we have done in the previous week. So let's move forward and go through these concepts one by one. Now let's talk about some basic object features, and the first one is the edge. And as you can see, the edges are the lines represent the boundary between two faces. So let's say that this is our object and these are the two faces. One face is this and the other face is this. So what will be the edge between these two faces? As you can see, this red line, this will be the edge between these two faces. So as we said that the edges are the lines that represent the boundary between two faces. So our object can change, the shape of an object can change. As you can see, this is a rectangular object, its cross section is rectangular, or its cross section, as you can see, it's a square. Sorry, its cross section is basically a square. Its cross section is basically a square. So in this case we will have clear faces, and in between these faces there will be clear edges. As you can see, this can also be an edge, this can also be an edge between these two faces, and this can also be an edge between these two faces. So the edge is basically the boundary between the two faces, as already mentioned. So now let's look at a cylindrical object who have a circle as a cross section. So the cross section of this object will be a circle. So there are two faces in this case, in this view. As you can see, one face is this one and the other face is the lateral face, the round lateral face that you see. So the only edge between these two faces will be between this face and the lateral face. So there is only one edge between this face and this face right here. So as you can see, this is a cylindrical object and its cross section will be a circle. So that's why it will have one face on this side, one face on this side, and the faces that combine this side face and the lateral face, there will be an edge between these two faces. So this is what an edge in this case will be for this shape. Then we have a round, let's say a spherical ball or a circular ball, or you can assume your tennis ball, for example. So in this case there are no edges because it is clearly round and it does not have any faces. So as we said that the edges are the boundaries between two faces. So we had faces in this scenario, we had faces in this scenario, but in this case there are no faces. So if there are no faces, we will not have any clear edges. So that's for this shape, for a ball shape. So in this case we will have no edge. Then there are corners, and corners, as you can see, represent the intersection between two or more edges. So using the example that we just given, what are the corners? Based on the definition, the corner will be the intersection of two or more edges. As you know, this is one edge, this is the one edge, this is another edge, and their intersection point is this one. So this will be the corner of this object. As you can see, the yellow, as you can see. So this is the corner of these three intersecting edges. And in case of the cylindrical object, as you can see, it had an edge, but there is no intersecting edge that actually intersects this edge. So it will have no corners. There are no corners for this shape, and similarly there will be no corners for this shape. So corners can only be found for prismatic shapes. As you can see, this is rectangular, so it had clear edges, and these edges had a one intersection point. So this is what we represented as a corner. This does not have intersecting edges because there are faces on the sides and a lateral face, but these two edges do not intersect each other at any point, so there are no corners. And similarly for this shape, it does not had any edges and it does not have any corners. Then there are surfaces. Surfaces are the boundaries are the areas that are bounded by edges or limiting elements. So we will be talking about limiting element in a while, and the edges, we already know what the edges are. Edges are these lines that separate the faces from each other. In this case and in this case, this was an edge, and in this case there was no edge. So surfaces are areas that are bounded by edges or limiting elements. So in this case, in the prismatic case, we had clear edges. In this case, we had clear edges and we had clear surfaces like this. So we can say that this was our surface, this was our surface, and this was our surface. Then what in this case we will do, in circular face, we do not have an clear edge that is representing this surface, this lateral surface. So what we will do, we will define a limiting element for it. We will define a limiting element for it that actually bounds this surface, and clearly for this there are no edges. So what we will do, we will actually draw a limiting element for it like this to actually bound this surface inside this limiting element. We already covered this in our lab, that for circular objects, for cylindrical objects, what we do, they will be represented as a rectangle. For example, in this case, if we project this on a plane here, if we project this shape on a plane here, it will be represented as a rectangle. Okay, so that's these two lines that you see, these are the limiting elements that actually bounds this surface, this visible surface that is being represented right here. So this is the function of a limiting element. When in case of no clear edges that should bound the surface, what we do, we define a limiting element to actually bound that surface. So now let's go through these examples, that these are the surfaces in this case for all the three examples that we just went through. This is these three surfaces, the visible surfaces. In the rectangular case, these are the surfaces in the cylindrical shape, and the surfaces for the ball case. So as you can see here, there are edges, there will be clear edges in this case, and we can clearly define our surfaces. So what we will do, we will need limiting element for this case and limiting element for this case to actually represent this lateral surface right here, and here in this case the surfaces that the limiting element will represent. So now, how is a limiting element defined? Limiting element is a line that represents the last visible part of the curved surface. So as we said that the limiting elements will be used for curved surfaces. Limiting element will be used for curved surface because here you can see that this is a curve. This is a curve. This is actually a curve. So what we will do, we will define limiting elements to represent these curved surfaces. So this is what we are going to do. Here we will draw two lines, and these are the limits. And these limits will be used when we project this shape onto a paper, and then this shape will look like a rectangle. So that's why it looks like a rectangle, because it will have any depth, but these two surfaces, these two edges in the projection will represent the limiting elements of this shape. So this is the limiting element for this case. So what we do in projection techniques, we already discussed in the lab that we will actually look at the object and the visible surfaces. In case of a cylindrical or circular objects, we will actually define their we will actually bound that visible surfaces by these limiting elements, as you can see right here and right here, these red lines. So these are the limiting elements, and again limiting elements are used to bound the curved surfaces, represent the last visible part of the curved surface. Then there is a projection theory, and in the projection theory, as we already discussed, is used to graphically represent 3D objects on 2D media. By media means a paper or computer screen. As you already did in the lab, that you will be given you were given an object, a 3D object, and what you did, you actually drawn 3 views of that object. That was the front view, that was the top view, and that was the side view. So this is what the projection theory gives us. Basically, this is the output of the projection theory, and now we will go through the projection theory, that what are the elements in the projection theory that actually helps us draw these 3 views. So the theory of projection is based on 2 variables. The first variable is the line of sight. It is the line of sight, and line of sight is an imaginary ray of light between an observer's eye and an object. So the line of sight is between the observer eye and an object. So let's suppose if this is an object, a 3D object, and this is the observer. So the line of sight will be between the object and the observer. And then there is a plane of projection. Plane of projection is an imaginary flat plane. It is an imaginary flat plane. Please note that the line of sight and the plane of projection are both imaginary, and we use these imaginary rays and planes to actually draw the views of our object. So a plane of projection is an imaginary flat plane upon which the image created by lines is sighted and is projected. So what we do, this imaginary plane is placed between the object and the observer, and where the lines coincide this plane, we actually mark those points, and then we join those points to actually get a view of that object from the side that we are looking at. So these 2 variables are used, the line of sight and the plane of projection, to actually in theory of projection. In the theory of projection, these 2 variables are used to actually draw the views of a 3D object. As you can see, this is the line of sight is an imaginary ray of light. As we said, this is an imaginary ray of light between an observer's eye and an object. So this is our object, and let's say this is an observer. Okay, and these are the lines of sight. They actually comes out from the corners. As you can see, these are my corners. These are the corners, and actually the line of sight originates from these corners, from the corners of this object. And in this case, this is the parallel projection. There are 2 types of line of sight. there are two types of line of sight. One is parallel. Here you can see that the lines are parallel to each other. These lines and these lines are parallel to each other. They are parallel to each other. And then there are one where the perspective projection, where the lines of sight are not parallel to each other, but they converge at a single point. This perspective projection is what is used by our sight center in our brain, that what we see in our daily life is basically the perspective projection of the objects inside our brain. So the parallel projection, in parallel projection the lines of sight is parallel to each other, and in perspective projection the lines of sight actually converge at a point. So let's see what will be the difference between these two. Then the second variable in our theory of projection is the plane of projection. As we already covered the line of sight, and we said that line of sight is an imaginary line that originates from the corners of the object, as you can see right here. These are the lines of sight. But the other variable is the plane of projection, is an imaginary flat plan which the image is on which the image is created. The image is produced by connecting the points where the line of sight pierces the projection plane. As you can see, this was the parallel projection in which the lines of sight were parallel to each other. As you can see there, the lines of sight are parallel to each other. So when these parallel line of sight pierce this projection plane, this is the projection plane, this light blue color, and when these line of sight pierce this projection plane at these points, what we will actually get the actual size and shape of this view, of this surface of this object on this plane right here. So this is the advantage of parallel projection that we had, and this is what we used in our lab, the parallel projection technique, to actually get the exact size of a certain side of an object. And in this case, this was the line of sight and the plane of projection are basically used to draw this view of this object. So if you are looking like from this side, so this will be basically the front view of this object, and the front view is drawn with the help of these two variables. One is the line of sight, and the other is the plane of projection. So these two can be combined to draw a view of a certain side of an object. So here, if you are looking from this side, so this will be the front view of this object. And as these lines are parallel, these lines of sight are parallel, these lines of sight are parallel. So on the plane you will get the actual size, actual shape and size of this side of an object. In perspective projection, the plane will be placed. These are the lines of sight, but the lines of sight are not parallel. The lines of sight are not parallel. In this case, they are basically converging at this point. So when they are converging, you will actually have an idea of the shape. You will have an idea of the shape, that what the shape of this side of an object will be, but you are not getting the correct size. The size is not correct. The size is not correct. You will just basically getting the idea of the shape, but not the side. And you can actually feel, you can actually experience that in your daily life, that when you are looking at an object that is far away from you, so it looks very small, but as you get near to that object, its actual size is getting clearer and clearer to you. So that's what is happening inside our brain, that in our brain, in that the side section, we have basically a side center inside our brain, and in that center what is happening is the perspective projection is happening inside our brain, and then we are seeing objects that are, we get the correct shape of the object but not the correct size with the help of perspective projection. And why? Because the lines of sight are basically converging at a point and they are not parallel. But in this case, in parallel projection, what we do, we actually keep the lines of sight, the imaginary lines of sight, parallel to each other, and by making them parallel to each other, we actually get the correct shape and size of the object. So that's why we use parallel projection technique. As you can see, that's why they are called parallel projection, and that's what we used in our lab to get the correct size and shape of our 2D views of a 3D object. Then there is also another type, that is orthographic projection. So Orthographic projection is a parallel projection technique in which the parallel lines of sight are perpendicular to the projection plane. As you can see, this is the type of a parallel projection. So we had before that two type of projection. One was parallel, one was perspective, but we were more interested in parallel projection because we had the correct size and shape of our view. So now there is another type of parallel projection, that is the orthographic projection. And in the orthographic projection, the lines of sight are perpendicular to the projection plane. So let's look at this example again. This is our 3D object, and this is our projection plane, our imaginary projection plane, and this is the top view of our object, and this is the top view of our projection plane. So if we look from the top, this is how this assembly will look like. The top view of our object will look like this, and the projection plane will look like this. So just to make clear what the orthographic projection is, we are making use of this arrangement. And what will happen actually in parallel projection technique, the lines will originate from the corners and they will pierce this plane at different points. So another line will originate from the corner, then another line, then another, and then another. So you can also see these lines in the top view, and what you are seeing, that these lines are making an angle of 90 degree, between this line of sight and the plane of projection are actually making an angle of 90 degree between each other. So that's why they are also called orthographic projection. So it is again a type of a parallel projection, and in that type of parallel projection, what happens is that the line of sight is making an angle of 90 degree and between the line of sight and the plane of projection, and this will also give us the correct size and shape of our view. So what you did, you actually used in the lab, you use the parallel projection technique, and in that parallel projection technique, you use the orthographic projection technique to actually draw the correct views of your 3D object. So then there are multi-view projections, and in multi-view projections, what we basically did in the lab was the multi-view projection, because as you remember, we cannot represent the whole information of an object with just one view. So we need at least three views. As you can see, this is the front view, this is the top view, this is the side view of this object. And as you already know that in the lab, we discussed that there are three principal dimensions of an object. And based on these three principal dimensions, we divided our sheet, and we first defined these three principal dimensions for our objects. And these three principal dimensions were the width, depth, and height. So if you know these three principal dimensions of an object, so you will be able to divide your sheet into equal parts, and then you will be able to correctly draw the views. So in the front view, if this is your observer and you are looking from this side, then in the front view, what we will get the width and the height of our object. Then in the top view, right here, the width will be common between the front view and the top view, and you will also get the depth of the object if you are looking from the top. And in the side view, from the side view, what you will get the height, and the depth. That's what we went through again and again in the lab, and again I will repeat here that we have three principal dimensions, and that is the width, depth, and height of an object. And based on these three dimensions, we are able to divide our sheet into equal parts and then draw our views. And some of the dimensions that are common between these three views are the width between the top view and the front view, that is common, and the height, that is common between the front view and the side view. So adjacent views is needed to fulfill the size description, just like this, that here in this case, if this is your object, so from the front you will get this shape, easily, but you don't know, you know the height and the width of this object, but you do not know the depth of this object. So the depth will be clearly shown from the top view. Because from the top view you now know the depth of the object, and you know that these are rectangular features. These are all prismatic rectangular features. So this information will be communicated by the top view, and then in the side view, what you will get, you will actually side view is not needed in this case for this object, but they have just drawn it to give you an idea of the side view, that the side view here are representing this edge right here, and this top edge right here. But two views are sufficient in this case to give the total information of the object given in this slide. Then to obtain the multi-views of a 3D object, there are two scenarios. In the first scenario, we actually revolve our object with respect to the observer. So in this case, our observer is stationary. Our observer is stationary, and our object revolves. And then another scenario is that our observer moves around and our object is stationary. So these two scenarios can be used to get multi-view representation of a 3D object. So in the first scenario, what we will do, we will actually revolve the object. So if this is your object, you will actually revolve it with respect to the observer to get the front view, top view, and side view. So let's go through that. If I am interested in the front view, then if this is my object, I will revolve it like this to get the front view of this object. As you can see, this is the front view. Then for the top view, this will be the side view. For the side view, I will again revolve the object to get the side view of this object. So this is the right side view of this object, as you can clearly see. And then I will revolve this object to get the top view. So now we have the three views of this object: the front view, top view, and the right side view. And as you can see, if you are looking from this side, so this will be the front view. This edge right here represents this edge, and this edge right here represents the top edge. And in the top view, what we are getting is basically that this edge right here represents this edge. So it is very clear, it is very simple object. And then in the side view, this will be our side view, so it is very clear. This will be our side view, right side view. So as you can see, our right side view will be in the L shape. So this is our right side view, and in this scenario, we are actually revolving the object and the observer is stationary. Then in another case, the observer moves around. The object is stationary and the observer moves around. So if for the front view, the observer will stand in front of this object and will look at it in this direction. And then for our imaginary plane of projection, and the lines of sight will be projected from the corners that we have. So this will be our front view. Then the observer moves to the right hand side, and the plane of projection and lines of sight are used to draw the right side view of the object. And then the observer moves to the top, and then again lines of sight and plane of projection is used to draw the top view. So in this case, the object was stationary and our observer was moving around to get these three views: our front view, our right side view, and our top view. So then we have the glass box concept, and in the glass box concept, as you know that a box will have 6 planes. So in the glass box concept, what we do, we place our object inside this box, and then we project the views onto the planes. So there are 6 planes in this box, and in every box there are 6 sides. As you can see, this is 1, 2, 3, 4, 5, 6. So what we will do, we will get 6 principal views of a single object. As you have already done an exercise in which we had a front view, a top view, a right side view. From this side we will have a left side view, from this side we will have our rear view, and from this side we will have our bottom view. So what we will have 1, 2, 3, 4, 5, 6. We will have 6 principal views, and the glass box concept is used to actually uh, take an object, place it in a glass box, and a box will have 6 principal planes, and then use the plane of use the sides of this box, use these planes of this box as your principal planes, and use the lines of sight to actually draw the 6 principal views of this of your object. So then what we do once the objects are drawn onto the 6 principal planes, then we open the glass box and we get the 6 principal views of this object. So this is the right side view, the front view and the top view that you are seeing. And once all the other sides are unfolded, what you will get are the 6 principal views of your object. And now you can see the bottom view, the left side view, the rear view. So this is the glass box concept, that you place your object inside the box and then you open the box, and once you open that box you will have 2D views on each face of that box. So you have 6 faces of that box, so you will get 6 principal views. As this is the again front view, this is the top view, this is the right side view, this is the bottom view, this is the left side view, and this is the rear view. You have already done an exercise in which the front view and top view were given, and then you drew a right side view, left side view, rear view, and bottom view. So if you remember that exercise, that those 6 principal planes were originated by the glass box concept. So this is the glass box concept to actually get the complete information of your object. As you know, we already mentioned that we need at least 3 views. We need at least 3 views. So basically 3 views are enough to communicate the shape and size of an object, of every object. So what the glass box concept does, that it basically gives us the complete information of all the views, the left side view, the right side view, the bottom view, the rear view, but we will have then to choose only 3 views to actually get our shape and size. So this was our glass box concept, that we placed our object, this was our object, inside the glass box, and then we originated these 6 principal views. And this was the front view, this was the right side view, this was the top view, the bottom view, the left side view, and the rear view. So these are the 6 principal views of the object that we had, and we got the six principal views by unfolding our glass box. And now you can see the dimensions that we can actually project. So the height is common between the right side view and it is common between the left side view. So this is the right side view, the left side view, and the rear view. So the height dimension will be common between these 3 views. And then we will have the width dimension. So the width dimension will be common between the front view, the top view, and the rear view. And then we have the third principal dimension, and that is the depth. And depth will be common between the top view and the right side view. So basically, just to give you complete understanding of the multi-view projection, this is how views are imagined, and this is how we get our 2D views from our 3D object. And this is another concept that is called the glass box concept. One was the orthographic projection concept, the parallel projection concept, and this is another concept in which we place our object inside the glass box, and then we project the faces of our object onto the planes of the box, and then we unfold the box to get our 6 principal views, and then we select only 3 views which are enough to give us our information of size and shape of our object. So this is what we have actually done. This was the 6 principal views that we get from our object in a glass box. So if this is our object, then we will actually project the faces. If this is the observer, so we will project the faces onto the planes of this box, and then we will unfold this box to get these 6 principal views of an object by using the glass box concept. And this is how the 6 principal views for this object will look like. This will be the front view, this will be the front view, again the top view, the right side view, the bottom view, the left side view, and the rear view. So you can see that the common dimensions, the width, the depth, and the height that is common between different views, and how these features, the different features that is being represented here. So in the front view, as you can see, in the front view, here there is a hole, and we know that this is a hole that because there is the center line between these two hidden lines, and this hole is actually representing this hole right here that is seen in the top view or in the bottom view. And this slot right here, this edge is actually represent this edge right here, this edge right here, and this edge will be hidden in this case if we look at the rear view. So the 6 principal use concept actually gives you a rigorous exercise. It actually put you under a rigorous exercise to actually exactly imagine and exactly visualize the different features of an object from each side, not just the 3 views, but from all the 6 sides of an 3D object set. How will they look like? So by going through this exercise, you will be able to correctly comprehend the different views of a 3D object, and you will be able to draw any 2D view. If there are only 3 2D views required, or there are 6 2D views required, then you will be able to draw them once you comprehend exactly that how will I represent different features in these views. Just like I went through these circles, that here this feature is representing the circle because here it is a center line. So now you can actually see that there is this hole, there is this hole that is being represented right here, and this hole is clearly visible from the top view. So the 6 principal use concept actually puts you under a rigorous exercise to actually comprehend the different features of an object and draw them on a 2D plane. Then there are projection systems, and in projection systems we already discussed these in the first lecture, and we said that these are actually the standards that are being followed, and they are basically related to how you align your views on your sheet. So there are 2 systems. One is the first angle projection system, the other is the third angle projection system. And as you can see that the first angle projection system is used in European countries, and it is also an ISO standard. But the third angle projection system is used in Canada, USA, Japan, and mostly in Pakistan too. So just to give you a rough idea, I've already drawn this. So for the first angle projection system, we will have a front view here, our side view here, and our top view here. So in this case, our views are aligned like this. So in the third angle projection system that you have followed in your lab was that there was the front view, then there was the top view, and then there was the side view. So here the views are aligned like this. But how we get these 2 projection systems, that's what we are going to look into. And basically we use our coordinates. We use our coordinates at x dash, y dash. So we use our coordinates, and we imagine these coordinates being planes, and then what we do, we actually project our objects, our views onto these planes, and get these 2 projection systems, that is the first angle projection system and the third angle projection system. So let's go through that. Let's give some space. So if these are your coordinates, and this is your first quadrant. As you can see, this is your first quadrant, and you are the observer. So as I said that this is your Cartesian coordinate system, and if we draw it like this, so this will be your first quadrant, this will be your first quadrant, this will be your second quadrant, this will be your third quadrant, this will be your fourth quadrant. So if we make planes in the first quadrant like this, and then place an object, and then project the views of that objects onto their planes, then we will get our first angle projection system. As you can see, this is our object placed in the first quadrant, and then what we will do, we will draw the views of this object on this plane, and on this plane. Then we will unfold these planes. So we will get a particular orientation of these 3 views. So that particular orientation will be called the first angle projection system. Then there is the third angle projection system, and in the third angle projection system, what we will do, we will actually put planes in our third quadrant. In our third quadrant, we will actually put planes in our third quadrant, and then we'll place our object there, and then ultimately we will project the views of that object onto these planes. And when we unfold these planes, we will get a certain orientation that will be called the third angle projection system that we already use. So if this is your Cartesian coordinate system, and then what we do, we actually make planes of these in the third quadrant, and then we place our object right here, and then we project the views on these planes, and then we will unfold them. We will unfold them, so we will get a particular orientation of these views, and so that particular orientation will be called third angle projection system. Then in the first angle projection system, again we place the object in the first quadrant. Then in the third angle projection system, we place the object in the third quadrant of our Cartesian coordinate system. And as you can see, these first quadrants and third quadrants, we have drawn planes, and these planes will be used to project the views of this object onto these planes. So this is our observer, and this will be the front view. This front view will be projected back onto this plane. As you can see, the lines of sight are used to actually project the view. Then this face will be projected right here, and this face will be projected right here onto our plane. So this will be our front view of this object. Then for the side view, okay, for the front view of the object in our third angle projection system, the observer will stand right here, and then the different features will be projected onto the plane with the help of the line of sight. So this will be our front view in this case. Now for the side view in the first angle system, the side will be projected on this plane. It will look like this, and then this face will also be projected, and this edge will be represented as dotted line because it is hidden. Then side view in this case will be projected onto this plane, and it will be the same as the one drawn in the first angle projection, and a dotted line to represent the edge that is not visible. Then for the top view, the observer will look from the top, and then the view will be projected onto this plane. Now this plane, and this. So this will be our top view. And in the third angle projection system, the top will be projected onto this plane. And these are the three views in the first angle and the third angle projection system for the object that is given. And what we will do, we will now unfold these planes. We will unfold them, and then we will have a particular orientation, and that orientation will be called the first angle or the third angle projection system. So now what we will do, we will actually unfold these objects along the folding lines that we have. We will actually cut them so that we can unfold them. All of this is imaginary, just to make you understand. We are not actually using a scissor, so this is just to make it clear to you. So this is how our front view, top view and side view will look like in first angle projection. Then the folding lines in this third angle projection system, the object, the planes will be unfolded along the folding lines, and this will be the front view, top view and side view in this. So this is how the first angle and third angle projection will actually look like. This is the front view, this is the side view, and this is the top view. And here this is the front view, this is the top view, and this is the side view. So now you can comprehend that why this is called the third angle projection system and why this is called the first angle projection system. And basically you can see that it is related to how these three views are oriented onto your sheet. So you can see the difference between the orientation, that here the front view is at the top right, then the left side is the side view, and the bottom is the top views. And here the on the bottom left there is the front view, and then on the top there will be top view, and then on the side there will be side view. So that is called the third angle projection system. And now you know that how these projection systems are basically, what's the theory behind this. And we basically use our Cartesian coordinate system, our first and third quadrants, to actually use and actually make these two systems. And what we used so far in our lab, we used our third angle projection system in our lab. And you can also use the first angle projection system. It is same as the third angle projection system, only your views will be aligned differently, like this. And in third angle projection system, you already know the views are aligned in this direction. And this is the 3D model of our object. This is the front view. This is the top view in the first angle and third angle projection system. And this is the right side view in the first and third angle projection system. So now you can clearly see that the orientation that is differentiates between the first and the third angle projection system of these views. Then we actually use a symbol. What we already covered in our first lecture, that we actually use different symbols to communicate that what is in some drawing, like the projection symbol is used to actually tell that what projection system are we using. Either we are using the first angle projection system, or either we are using the third angle projection system. So just to tell anyone that what we are using, we actually use a symbol to actually give them an idea that what projection system are we using. And for that symbol, we will use a truncated cone. We use a truncated cone, and we take a truncated cone, place it in the first quadrant, draw its two views, and what we will get a symbol for a first angle projection system. So this will be the right side view, this will be the front view of our projection system. Then we will unfold that, and this is what we will get. This will be our symbol for our first angle projection system. Then for the third angle projection system, we will take the same truncated cone, we will place it in the third quadrant, we will project its front view and side view onto the planes, we will unfold them, and then we will get a symbol like this. So in the first angle projection system, you can see that the concentric circles are on the right side, and the longitudinal view of this truncated cone is on the left side. And in the third angle projection system, the concentric circles are on the left side, and the longitudinal view of our truncated cone is on the right hand side. So this is the main difference between the first angle and third angle projection symbols that are used. And we basically use these symbols on drawings to tell anyone that is reading the drawing that actually which system, which projection system are we using. Either we are using third angle projection system or the first angle projection system, and we will communicate that information with the help of these two symbols.